Stoke's theorem is the last integral theorem that we're going to take a look at, and it's like all integral theorems, it gives us two ways to look at the same picture. Now we're going to start with an integral that we've seen a lot now. It says, this is basically our work integral. The integral of f dot dr is equal to the integral over a surface of the curl of the field dot in ds. Okay, so we got a few definitions to go through here first. Now first off, what are the c and the s? Well, the surface here is any surface that has, let's just kind of do something like this, that has a boundary that is a simply closed curve. So think of like our paraboloid here. The boundary of that surface is a simple curve. So that's what S has to be, and C is the boundary. So C is a simple closed curve that is the boundary of S. Okay, so that tells us what S is. S is the surface, and C, of course, is the boundary of that surface, and it's got to be simply closed. F is the field that exists in this area. N is a little bit tricky. Now, when we do this integral, we're going to stick with the going around in the counterclockwise fashion, which means as we go around our curve C, we're going to go around with our left hand on the inside. Well, that also helped us define what N is, because the surface is going to have some orientation. We need to know which normal to use so that this relationship is true. Here's the way you do it. It's the right-hand rule. Think about using your hand and following it around the curve. So as it follows around the curve, your thumb points in the direction that the normal should be. So you see, this one would basically, the way we're looking at it, would have some upward normal. So as long as these things are true, this relationship would be true. So just like before, we're going to do this by showing both pieces. So again, anytime you're told to prove a theorem is true, you got to do both sides and show that you have the same value. So let's come up with a region and see if we can do this. For the first part, we're just going to do the line integral that we've done in the past. So find this value for f is equal to our field. Let's use negative y squared z and x. And let's C be defined to be the intersection of, let's do the same curve that we did in the past. This is easy to do. Z is equal to 6 in the first octave. Now what I mean by that is it's a little bit different than what we've looked at in the past. So this was 1, 2, 3, 1, 2, 3, 1, 2, 3, 4, 5, 6. So when we draw the picture here, what we're actually talking about is just the intersection with the coordinate planes. So our curve C here is just the lines. Now again, if we're going to traverse this, we got to traverse this in the counterclockwise method. The surface itself that we're going to be doing in the second half is actually the diagonal plane piece here. So we'll get that in a second. So if we want to do this line integral, we got to find the integral of f dot dr. We really want to think about this as three different curves. Let's see, C1, C2, and C3. There's X, Y, and Z. So we really have three integrals to do for this. So let's do the parameterization for each three, and then we'll kind of do the line integral. So I'm going to go way over here real quick. For C1, what could the parameterization be? Well, if you kind of think about this in two dimensions, in the XY plane, this thing goes from here to here, right? As we move here, we're going from the x-axis to the y-axis. So we're going in that direction there. Now notice we're basically working with threes here, so it may be really helpful to let our parameter go from 0 to 3. I'm going to start just a little bit. So let's say our C1 here, R of t will be, all right, in the x direction, x goes from 3 to 0. So we need to run this backwards, and we've seen how to do this. So we're going to go 3 minus t in the x direction. Y just goes from 0 to 3, so that would just be t in the j direction, and we don't move it all in the z direction because we're in the xy plane, so all the z's are 0. So let's just move that up. So this is 0 less than or equal to t less than or equal to 3. So that would be the parameterization we're going to do here for C1. For C2, let's go ahead and do that parameterization, r of t. All right, so C2 is the, and we're in the YZ plane here, so let's draw that part of the curve, maybe a little bit easier to see in 2 dimensions. So if we're in the YZ plane, we're going from the y equals 3 right up here, 1, 2, 3, 4, 5, 6 to here. So we're going in that direction. Now again, we have our bounds of 3 and 6, so I kind of like the 3 thing. So if we, again, let our parameter run from 0 to 3, all right, what's going to happen? Well, y again goes from 0 to, from 3 to 0. By the way, x is 0, of course, xi. So the y goes from 3 minus t. And the z, what's the z going to run from? Well, that goes from 0 to 6, so that's twice the value. So this would just be 2tk. Okay, so no x value because we're in the yz plane. The y goes from 0 to 3, that would work, and the z goes from 0 to 6. That seems to work. All right, so let's take a look at C3. C3 is the part in the xz plane. So when we're kind of coming back down this way. So let's go x and z. Let's see, 1, 2, 3, 1, 2, 3, 4, 5, 6. So we're going from there to there. So from the z-axis to the x-axis. Again, I kind of see these 3 things happening. So I'm going to guess I'm probably going to run my parameter to 3 again. X is an easy one. X just goes from 0 to 3, so that's just t. There are no j's because we're in the xz plane. What does z run from? Z runs from 6 to 0. Well, I've got to go backwards, so we want to start at 6 and go to 0. So since that's twice as big as our parameter, we're going to go to 6 minus 2t. Notice when t is 0, we're at 6, and when t is at 3, we're at 0. So the z equals 0 here. So those are the 3 parameterizations for this region. So let's see if we can find the actual integrals for each one of these. So just for a note, so I have this for later. Let's say f was negative y squared zx. Let's just put that over there for a second. All right, so let's do the line integral for each one of those and see what we end up with. So for our first one, we're going to do the integral for C1 of f dot dr. So on C1, f is going to be equal to, see, on C1, x is 3 minus t, y is t, z is 0. So f is going to be negative y squared, y was t, z was 0, and x was 3 minus t. dr, well, dr is going to just be the derivative of the r, so that's going to be negative 1, 1, 0, dt. So we're going to integrate from 0 to 3, because that's what t runs from, that's our parameter, of f dot dr. I think we can do this pretty quick. Negative t squared, negative 1 would be t squared. 0 and 1 is 0. 3 minus t and 0 is 0, dt. And that's pretty easy to do. That's 1/3 t cubed from 0 to 3. Top endpoint minus bottom endpoint, t cubed minus 0, so that's just 9. Okay, so let's put this over here. The value from our integral for C1 is 9. We can fit C2 right here, I think. Let's go ahead and do it here so we can leave it up there. So the integral for C2 of f dot dr, well, on C2, f is equal to, well, on C2, x is 0, y is 3 minus t, z is 2t. So this becomes negative y squared, z is 2t, and x is 0. dr, the derivative of our path, is going to be 0, negative 1, and 2. dt. So the integral of f dot dr is going to be f dot, again, let's just do the dot product, negative 3 minus t squared times 0 is 0, negative 2t times negative 1 is negative 2t, 0 times 2 is 0 dt. All right, again, a fairly easy integral to do, so we get the integral from 0 to 3. Well, let's just go ahead and integrate it. That's going to just be negative t squared evaluated from 0 to 3. Top endpoint minus bottom endpoint, so negative 3 squared minus 0 gives us negative 9. So the integral for C2 is negative 9. All right, I'm going to go back over here and erase this one. Let's do the last path. This will get us all the way around. So the integral for C3 of f dot dr, well, on C3, f is going to be equal to, on C3, x is t, y is 0, z is 6 minus 2t. So f becomes negative y squared, so that's 0. 6 minus 2t is the z, and x is t. R, dr, the derivative of our path, is going to be 1, 0, and negative 2, t. So our integral, again, our t runs from 0 to 3. F dot dr, what do we get? We get 0, 0, negative 2t. Now this is the exact integral we just did a second ago, so that is negative 9. So we now know the integral for C3 is negative 9. So if we add up all of our paths now, I'll stick it right here. So the integral around C of f dot dr is going to be the integral for around C1, the integral for C2, and the integral for C3, which is 9 minus 9 minus 9, which is negative 9. Okay, so that's taking a look at Stoke's theorem, looking at the line integral that was on the left side. In part 2, we'll come back and we're going to take a look at the surface integral of the curl dot n ds.